Welcome back. Last chapter we looked at magnets, and we ended the chapter by looking at how magnets could exert forces on other magnets, and that was caused by the interaction of internal and external magnetic fields. In chapter 22, we're going to look at how we can use those forces now to create currents. Because remember, we get a magnetic field from a moving electric charge. So now we're going to look, can we use a magnetic field to cause a charge to move? Okay, so that's on chapter 22, induction and alternating current. And it was, again, Faraday that kind of proved this. Remember, Oersted was the one that proved that moving electric charges created magnetic fields. Michael Faraday, along with an American, Joe Henry, simultaneously proved that you could do the reverse as well. That if you can have a magnetic field generate an electric current. Now, the diagram we're going to use, very similar. I'm going to use one like this that's over on the corner, but also want to draw another one. That if I have here my, oops, erase that part off. If I have my bar magnets, so I have my magnetic field going through, or going across. And now if I take my wire conductor, remember we drew something similar to this before. And when we said, hey, if there's a current going through it, it generates a magnetic field, and that magnetic field interacts with the other one, and therefore we get a force. Now what we're going to do is going to do the reverse. So we're going to force this conductor to move through those magnetic field lines, to cut through those magnetic field lines. And in the process, a current will be generated in that point in time. So a current will come on out. Okay, so what Faraday did, this is the very first thing he did, almost the exact same diagram, but by moving this, by causing this a velocity to move this up through, by forcing it up through, it cuts through the magnetic field lines, and a voltage, a current, is created in that conductor. Another way to look at it is this, okay, that we can take a bar magnet, and if we move it in to cut through across those wires, we will generate a current in that wire. Okay, what it comes down to, though, is at the end of the day, well, the main point is that we have to cut through those magnetic fields to create a current. Okay, so moving electric charge. We have to cut, must, oops, let's try that again, must cut through the flux lines. And this was also shown in the fact that if you go back up to this, we noticed that the conductor would produce a maximum amount of current when it's moved perpendicular to the magnetic field. So it actually would cut through those magnetic field lines. However, if we moved it parallel, so it wasn't cutting any lines, there was no current produced in it. So again, it has to come back down to this, and I'll put a little star next to it. To create that current, to create that voltage, create those moving charges, you have to have your wires cut through those magnetic field lines. Now, it doesn't matter if you move the wire, like we did in our first example up here, we move the wire cutting through those magnetic field lines, or if we have, like down here, we cause our magnet to go through, so the magnetic field lines are cutting through the wires. Sorry, I said that backwards. The magnetic field lines are still moving across those wires. So it doesn't matter as long as those magnetic field lines are being cut. That is what creates that current. Okay, so remember, and I'm going to make the adjustment here. I've kind of mentioned voltage, I've kind of mentioned current, and all those other stuff. Okay, we have said in previous chapters that in order to create a current, we needed a source of energy in order to get those charges, to give them the impetus to move. Okay, in previous chapters, we always used a battery, and that produced chemical energy, or took chemical energy and created a potential difference and got that electrical energy that we needed in order to cause those charges to move. We now have a way by using mechanical energy. Okay, so this is by using mechanical energy. in order to create that voltage, to create that impetus, that energy per charge for those charges to move through. Okay, so remember, in order to have a current flowing, you have to have that source of energy per charge, that voltage, that EMF. We had batteries before. Now we have another way, a mechanical way of doing it. Now, this induced EMF, Faraday found that the magnitude of the EMF induced in the conductor, the voltage induced in the conductor, depended upon how quickly you cut through those lines and how many lines were actually cut. Okay, and so what he kind of wrote out was that the EMF, now I'm going to use the EMF, we use this instead of voltage, but for our purposes, this is basically voltage, is equal to the number of flux lines cut in a unit of time. Okay, so this is the number of flux lines. And obviously this is time. And there's one other thing on here too. I'll put it out front. There's an N, okay? And that it refers to the number of wires that are being cut. So this is the E, that delta phi over delta T is for each particular wire that's being cut, and it would be the number of wires that are being cut. Because if you cut through with one wire, and then you cut through with two, you're gonna get double the amount, okay? Now, there is a negative out in front. And I'm going to put a little black negative here, okay? That negative refers us back to something called Lenz's law that we will discuss tomorrow. And the fact that when you create this voltage, the voltage is created directly opposes the change that created it. And we're going to go through that in great detail tomorrow. Okay, I've got some other demonstrations and stuff that we'll do. Okay, and so basically what we can say is we can actually rewrite this formula too. And Faraday showed that the EMF, another way to write it, is equal to, again, to the negative of NVBL. Okay. Actually, let me get rid of the N part because we don't need to have that. It's equal to the negative VBL, where V is the speed of the cutting. B is the magnetic field strength. Can't write. You get the idea. And then L is the length of the wire that's being cut. Doing the cutting. Okay. So these are two different ways. And so all of this comes down to, we can change that like the wire, we can change the field strength, we can do all that. But regardless, when we do this, we are physically moving. We are causing either the wire to move through the magnetic field and have those wire cut through those magnetic field lines, or we are physically moving the magnet across those wires. And so in the process, we are taking our mechanical energy and we are converting that into electrical energy. Now, we're going to go into more in depth. I've got a couple demonstrations. I've got a couple websites that we can go look at that'll show this a little bit more, okay? Because this does sound a little confusing, okay? But at the end of the day, the key thing you have to remember is that we now have another way to generate voltage, another way to generate current. We don't need to have a battery anymore. We can have something else. We can cause a magnet to move across the wire, and in the process, that will generate a voltage, create a current in it. And this is the foundation for the thing that we're going to talk about tomorrow, generators. So everybody have a great night. We'll see you later. Bye.